Okay, I think next week, midterm. Okay. I would like to finish off last discussion and maybe a few examples, and move to next section, which is optimization and antiderivative if we have time. Okay. And maybe at the last part, maybe around 15 to 20 minutes, maybe I will show you the last year questions. And then I think I will attach the questions in the Moodle section so you can have practice. Okay. And we're going to have more practices next Tuesday, also on your TA class. Okay. Okay, so we have this conditions. Okay, so we have a f is a positive function. Okay, and we have limit that is when x approaching a of the function of x, it will be equal to 0. Okay, wait for a moment. Okay. Okay, and then we have the limit for the g is going to be infinite. And then we would like to approach the limit of f with the power of g. Okay, so this is, we call the 0 with the power of infinity. Okay, so we start by taking the, so let's write in terms of y. Okay, and then as usual, we take the log for both sides. So we have both. We have ln. Okay, and then we can move the g to the front. Okay, remember that the function f, in the description, the f is a positive function, right? Okay. So perhaps this log, because f is positive functions, then the ln f of x is defined on the interval. Okay. And so if we are trying to sketch the curve, for example, let's say this is just a random sketch, but suppose that this is our ln f of x. Okay. And then we can take the limit. Okay, take the limit for the whole system. So this will be, so take the limit. If you see from the curve that I would like to show you, that is if the limit of g is infinity and the limit of the f of x is going to be 0, then what will happen? What will happen? So imagine that this is known, this is we have in the description, this is also in the description, but how about the ln? Ln that is going to be 0 you see what we have here. If we try to imagine that it's going to be down here, right? So suppose that this value is negative, right? Okay. So from these two description, then the whole thing here with the additional log, this could be this, okay? Or let me write down here, that is because due to that the limit as x approaching a of the ln, this is negative infinity. We could start to maybe taking some other variable to give maybe better description. So let t is equal ln y, okay? So let t is equal ln y. So y, we can write y is e with power of ln y, right? So we can write limit as t approaching a, or maybe let me start from x, from the beginning like that, and then we can rewrite this in terms of negative infinity as we mentioned from here. Okay. And then we can write this as e, this is ln y, so we write t, and this will be 0. Okay? Or we can also trace the curve. So tracing the curve, suppose that this is just illustration, okay? Let's say this is the e, okay, e to the x, and the other side, let me, okay, let's say this is the e to the negative x, okay? Just a normal exponent, okay? You will see that since if we increase, okay, you see that it's going to be infinite, and if we move this e to the x to the left, it's going to have the asymptote and the 0. If we flip the curve and then start by taking the negative x, okay, now it's, when it's going to be positive, it's getting 0. And then if we take to the left side, it's getting infinity. So if we write it in terms of e with power of t, and then we take t to the left side, then it's going to be 0. Okay? So that means from this concept, then, and from here, we can write that limit with power of g of x, this will be equal to limit of e, and then we write g of x ln f of x.
Good morning.
What happened? What's happened?
Lots of things. I'll explain to you later.
Oh, okay.
You sure?
No, I'm
You can move.
Do you start?
Is it okay?
Yeah, it's all good. Yeah, it's all good. No, don't worry.
Obviously, it's not okay.
No, but it can be better.
Okay. Okay. So we can write. So let me continue a little bit. So since this is going to be negative infinity, so e with power of negative infinity with the limit, we can trace back and then we get this 0. So this will be equaling to, or maybe equaling to 0. Okay. Another description, maybe to help you to understand this e, I think, because you will see this a lot later on. You could also think that if we have e to the negative x, this is equal to 1 over e to the x, right? So this is actually, if we take limit for this, the limit will be 0, right? So this limit is 0, okay? So it means at the end of the day that it's proven that this limit for the f of x g of x, this is equal 0. So this is if limit 0 and limit of g is infinity. So the idea is, I think the important thing here is the first step here. So f is positive function, and when we take the ln, then the whole ln f of x will be defined because f is positive function. And then we could try to draw the ln. Okay. So suppose that this is the ln that we are going to have, that is going to be negative infinity as we move to some point that makes, perhaps in this point, it's making it 0 for that point. So it's going to be negative infinity. Okay. I hope you understand this part. Okay, this is the crucial part is here. The rest is just filling in the mathematical notations. But the conclusion is the indeterminate forms 0 with power infinity is actually determinate. Therefore, for every 0 with power of infinity, it will be 0. Okay, maybe some example. Okay. Okay, some example. Okay. Example for the indeterminate forms. maybe just 2 questions. Okay, so let's solve this this limit. Okay. So this is, if we take 0, this will be 1 with power infinity, which is indeterminate forms. Okay, so we take the we can write in terms of e if you want. So e with power of the ln. So this will be 1 over x and then ln. Okay. And then we can move the limit to the upside. So e and the limit. And now we have the condition for the 0 over 0. So we can take the L'Hopital rule for the limit. Or maybe let me write here. E and then take the L'Hopital. So every time you do L'Hopital rule, don't forget to write the LH so that you are telling the audience that, okay, we are doing L'Hopital now. Okay. So doing L'Hopital, this will be 1. This will be 1 over 1 minus 2x multiplied with negative 2. Right? So this will result negative 2, or this will be e with power of negative 2, or 1 over e squared. Okay. So we only need one L'Hopital. Right. Now the second one, I think I will just focus on taking y first. So taking y as 1 minus cosine x with power of sine x, and then taking the log both sides. Okay, because I think the second one will be a little bit long, so I will just describe this. So ln y, so we have, this will be sine x ln 1 minus cosine x, right? And then taking the limit, this is limit. If we check the limit, this is 0, this is 1, 1 minus 1, 0. So log ln 0 is infinity. Right? So infinity 0 is a multiplication. It's an indeterminate product, which means the only way to solve this is to force this arrangement become 0 over 0 and infinite over infinite. So for most of the case, if you get any indeterminate forms, your goal is to make it 0, 0, or infinite over infinity. Okay. So I think the only possible way, because this is already in one big functions, ln with some other function inside, I think we can focus on the sign. So we can take sine and then write 1 over sine theta or cosecant. But me too, I don't really familiar with that, so I just write 1 over sine. Okay? So we can write limit so if we take 0 inside, this will be infinity, this will be 1 over 0, which is another infinity. So infinity, infinity, then we can apply our L'Hopital. Okay? We can apply for our L'Hopital. So take L'Hopital. So taking the 1 over 1 minus cosine x, and then derive negative cosine. So it will be negative sign, so this is sine x over there. And then 1 over sine. What will be 1 over sine? I think let me write here, just so sine squared. This, right? So we have negative cosine x over sine squared x. Or you can write negative cotangent cosecant, right? Okay. But anyway, so let's arrange the equations. I think we can write 1 minus cosine x. This will be sine squared x and cosine x, and then I will put negative here. I'll put negative in the front. Okay. Okay. What else can we do? So this is sine cube, and then we have this. Okay. Yeah, I think we'll just multiply. Okay. So limit. So negative in the front. Let me just write this and see what will happen. So this will be, okay, if we put 0, so it's still 0 over 0 still. So maybe one more L'Hopital. But can we do something about this? Tangent. Yeah, maybe take some L'Hopital. Okay. Okay, then do another L'Hopital. So the top one will be 3 sine squared x, and then multiply the chain rule cosine x. And the bottom one will be let me make it the middle here. Okay, so product rule, sine cosine x cosine x. And then plus 1 minus cosine x minus sine x. Okay, a little bit more. Actually, I already have the answers to cancel, but I will write one by one. So 3 sine squared x cosine x this will be plus cosine x minus 1, right? Okay. Okay, now check the 0. So this will be 0. This will be... Oh, wait. We cancel first. Cancel this. Cancel with this. Okay? And then check. So check 0. This will be 1. This is negative 1. It's still 0. Wait. Cosine x. So 1. This is 0. Oh, yeah, 0 over 1. This will be 0, right? Okay. But we have not finished yet, so limit of this is e ln y, which is e to the 0. It's 1. Okay, so a little bit long, but somehow we can take L'Hopital rule twice and we get the answers. Okay, any questions? Any questions? Perhaps you are confusing about how this is going to be. Any confusion? Yes. The first one.
When you have
The first line. Even the first line. The first line.
and then the rest with the cosine, the negative cosine over sine squared.
Yes. This one from 1 over sine.
Yeah. So, wouldn't that just be 1 over the derivative? Wouldn't that just be 1 over cosine?
How?
Because the derivative of sine.
The same as this, right? What's the derivative of this? What's the derivative of this?
Negative.
Yeah.
Negative 1
Over.
over.
The same or not?
Okay.
Okay. Get it? Okay. Any other question? Okay. Let me tell you that this is a typical standard question. Okay, so you need to be able to use something. We'll be giving you more, but later. Okay, we'll be giving you more, but later. Yeah. I will show you like the first is the last year midterm, what it looks like, and then perhaps if we have more time, we can go for another exercise. Okay. But before the break, I would like just to show you the next part of the section, which is the optimization problems, which actually related to the our maximum minimum problem. So if you remember, I think either in the junior high or maybe in the senior high, you are usually have questions like, I have a box, I want to put some water inside, or maybe some, and this has some volume, with some volume, and how to maximize the box, okay? And I have the, like you have the cardboard, okay? You want to build a box, and you need to fill in some water. You know the volume of the water, and then you have some limitation in your cardboard. How to maximize so that the most water will be filling in. I think similar with that, right? You have those questions, similar to that question. So we are going to see for more details, because it is actually one application of the maximum minimum. Okay. So before looking at the midterm, so let's say we are going to have the optimization problem. Okay, no need to read this, but let me just show you. This is some steps that is in your textbook, but I will simplify this to make it more easy, okay? To make it more understandable, okay? So first, you are given a problem, a set of problem, okay? Okay, so first is the problem, and the second, so first, let me write here, just a summary, okay? So you have a case or problem that somehow this case, it will relate it to critical point, okay? Critical point. Critical point is related to finding the max or min value, okay? And this is actually our goal, okay? To find what is the maximum value, what is the minimum value, okay? The second, what you need to do, the first thing is usually you are going to draw some diagram or some sketches, either the geometric or maybe some curves, okay? And then usually you are going to name the variables, because the question usually doesn't give any variables, so you need to use by your own name, okay? X, Y, Z, anything. Third is find relation. So find relation between all the information given. Okay? Either it can be formula or any models. Okay. Okay. Maybe the question is already given you some equation to work with, so you can use that as well. And finally, 4 is finding the max and min value, which usually we need just to derive once and equaling it to 0. Which this is, the x is actually our critical point, right? And if you remember, when we have the critical point, we can know the max or min value. And if you understand the core concept in this optimization, in your textbook, if you read the questions, you will understand why the question is asking, one question asking maximum, why the other question only asking minimum. Okay? Because of the first derivative. Usually they only have this possibility, like that, you have maximum, or you have minimum. There are, I think, usually there are not many cases that has both minimum and maximum. Usually they don't give that kind of problem. So usually either max or min. And the questions within the textbook, if you read the question, they will ask the right question. They will ask, for example, what is the minimum? Which means that You just need to make it 0 and then find the x, and then that x will have the minimum value. Okay? I will give you some reason and how to know the core concept. Okay? And when the question is wrong. Okay, when the question is wrong. Okay, I will give you later. Okay. So I will just give you the idea with the example. Okay. I think that will be a better. Okay. To have a good applications. So let's say we have if 1,200 centimeter squared, sorry, of cardboard is available to make a box with square base and let me use a different color and open top, which means you have a box without the top. Okay, open top. So find the largest possible volume of the box. So we have this problem. So first, you can maybe underline which one is the highlighted points. The first is the limitations. So you have we say it's constraint or limitations. Okay? We have only 1,200 cardboard, okay? Which means that if you want to make a box, the only way is to cut from this 1,200, right? So actually, we need to know how we are going to cut. How will be our design? Okay? Like how long? Okay? And we need to make the square base, so it's square, and open top, so without the top. So we can draw the geometric. Okay, we can draw the geometric. Okay, let's say that's the square. So, and then we can name the square. Let's say x and x. Okay, and we have different height. Maybe let me move this a little bit down. Okay. And then let's name this y. So this is no top, right? So our goal is to find the volume. The volume. So our goal is the volume, which is x squared y. We call this is, we want to optimize this. So this is the optimization. Okay. And then we have this 1,200 cardboard. So we are going to add all the area, which is having the total area of 1,200. Okay. So the area is x squared, right? And then plus 1, 2, 3, 4. So we have 4 xy. So this will be equal to 1,200. Okay. So this is what we call the constraint or limitation. Okay. So what will we do next? The next thing, this is our optimization, right? This is the one that we are going to derive. But we have two variables. But we have this relation. So our goal is to find the relation and then make this optimization only one single variable. Okay, I think we can do that, right? So we can write for example, we can write from here that 4xy is, and we can write y and divide by 4x for all these terms. So 300 divided by x, and then minus x divided by 4. Okay, and then using this y, we can exchange to this y, okay, to the volume. So volume is x squared and then multiply with 300 over x. Okay. So we have 300x minus x cubed over 4. Okay. Now this is our volume. We have this is the function that is available for us to derive. Okay. And then we are going to find the first derivative of this, because we would like to find the critical numbers, right? The critical point. So the v prime, so we are going to derive this. Derive with respect now to x. So 300 minus 3 over 4x squared. And make it 0 to find the critical point. So 3 over 4 x squared is equal to 300. We can cancel this. So x squared is 400, which means that x is 20. So it cannot be negative, right? So we exclude the negative answer. So x will be 20 centimeter and y is 300 divided by 20 minus 20 over 4. So y is 15 minus 1, minus 5. So it's 10. So we can conclude here, largest possible volume when x is 20 centimeter, y is 10 centimeter, and the volume itself is x squared y, which is 20 squared 10. This will be 4,000 centimeter cubed. That's the largest possible. Usually, my midterm always include the optimization. Usually. But for now, I will make the optimization into the next one. Okay. Here? Okay, so first is understanding the problem, highlighting which one is our goal, which one is our goal. Take the diagram, name the variable, find the relation, find the constraint, find optimization, derive one time, equal to 0, find critical number, and that's it. And most of the questions just like that. Draw diagram, name variable, first derivative equal to 0, and then you get the value. This one? Or this one? Oh, that is from x squared plus xy, 1, 2, 3, 4. Okay?
It's not too close square because it doesn't have the.
Yes, the tops. Yeah, yeah. We remove the top. So again, it's based on what kind of question you have. Like, if it is having a complete box, then it has a top. But it doesn't say like it says that it's opposite. So we are removing one on the top. So we have this area also. Okay, let me give you one more example and to see how we could cope with this. Okay, now go back to this one. Okay, so I hope you get the question correct. Okay, so the wire 1 meter. Okay, wire 1 meter, and then cut become two pieces, and then each piece encloses a square. So we are going to make a square from the wire that we cut. And then it needs to, so you need to calculate the largest area, and the largest area, which means we are going to let's draw the area first. Okay. So suppose that we have 1 meter. So let's say this is 0, this is 1. Okay. So we cut. Maybe not really in the middle, maybe a little bit on the right side like that. And if we name this distance x, then the other one will be 1 minus x. Okay. Okay. If you name this x and you name this another maybe y, it will be maybe not really happening. Because we know that the whole distance is 1 meter. So we need to name it as 1 minus what we are going to name it, okay, 1 minus x. So from this x and 1 minus x, we are going to make a square. So let's make this. Let's say that's the square. Not really square, but maybe, yeah, that's the square. The square will be having a side x over 4 and x over 4, right? The same thing with 1 minus x. Let me. Okay. So let's say this is 1 minus x over 4 and 1 minus x over 4. Okay. So this is the constraint. Okay. And the optimization is our area. So optimization, so find the largest area is with meaning that we are going to add this and make it largest. Okay? Make it largest. So the optimizations is the x over 4 squared, okay, and then plus 1 minus x over 4 squared. Now, if we are moving towards what we did previously, this is going to be the a prime, which is the derivative of the a. So we could do that. This will be x squared become 2x over 16, which is x over 8, the first one. The second one, we are going to have negative 1 minus x. This is over 8. Okay. You can think this from 1 minus x squared, and then we can derive this, become, and then multiply with the negative, right? So that will be negative. So 2 with 16 become 8. Okay. And then we can maybe take it 8. So x minus 1 minus x. This will be 2x minus 1 over 8. And then we are going to equaling this to 0. Okay, equaling this to 0, which means 2x minus 1 over 8 is equal 0, which means that it seems that our critical number is 1 over 2. Our x is 1 over 2. If we try to make the area with 1 over 2, so this will be 1 over 8, right? 1 over 8 squared plus 1 over 8 squared, which is 1 over 64 plus 1 over 64 is 2 over 64 or 1 over 32. Question is this the largest area? Okay, so this is when the question is actually wrong. It's not asking the right question. Actually, if you remember what we did in the sketching curve, okay, in the first derivative test, we can take the line number and put the 1 over 2, okay? And then checking to the first derivative, if we check 0, let's say 0, we will have a negative. We check maybe 1, or maybe, maybe 1, it's positive, right? So we have negative and positive. So 1 over 2 is actually a minima, right? A minima, okay? But can we try to answer the largest? There is some way, but it will include limit. So the answer is a little bit abstract, but I hope you understand the point. Okay? So we can take, for example, let's say this is a function. For this, let's say this is 1 and then this is 0, the limit, right? I mean the left and the right, the wire. Okay? We have 1 meter. So we could say that if we take the limit as x approaching 1 from the left, okay, of the function, which means that it's going to be getting close to 1, which means that the other part of the wire is somehow, actually we remove that. So we take 1 and then the other one will be 0. So will be 1 over 16, right? 1 over 16. So if we take the limit within this, we get 1 over 16. The same way, we can take the limit on the left side, taking it for 0, okay, taking it for 0 for our function. And then we could see that if we take 0, then this one will be 0 if we take the limit, and this will be 1 over 16. So perhaps it's a little bit, I call it a little bit cheating. So perhaps, I will write maybe 1 over 16 is the largest area with the help of limit. Okay. Of course, in the real world, if you cut something that is really near 0, almost impossible maybe. Maybe almost impossible. If you cut, somehow we still get maybe it's not clear 1 over 60, but maybe close to 1 over 60. So that's the only way we can approach it, I think, with the help of limit. But don't worry, your problem set in the textbook, they ask the right question, so you don't need to check again. If they ask about the minima, it means that the critical point will be the meter zone. So this actually, the smallest possible area. Oh, maybe let me zoom out. Okay. So it's actually, the optimization is still related to what we have done before. We check the first derivative, the minima, the maxima, critical point. The difference is we apply that into some set of problems. We are given some information. We are trying to draw a conclusion from the information. First, we draw the diagram. We name the variables. We set some relation between the variables, okay? And then we take the derivative, and then do the first derivative test, and then we have the critical points, and check the critical points, and then we get the values. Most of the problem will be with that algorithm, okay? So in that order, okay? Draw, name variables, and so on and so forth. Always similar. Okay? Do you think it's simple? Easy? No? How do you think? What do you think?
I always take class in high school when we come to doesn't have that high school, like, oh, you cannot
Yes, yeah. We see it again and in more detail with the calculus. Okay. I'm considering like if we are getting this in the midterm format. I think no. I think no. Okay, I think no. Yeah. You can pray. I'm not going to take this into midterm. Okay, actually my plan is I will take you to the introduction of antiderivative. That is going to introduce you to integration. But I think that will be for Tuesday, for some part of Tuesday, and then the other part will be practices. So now I will going for practices, just to see how much concept you can understand. Okay. Okay. Are you ready? No? No. Don't worry. No, I'm just showing you the last year midterm. So every midterm, every exam, like from 4 years ago, it's a little bit downgraded. I adjusted several times. So okay. Later I will put in the model so you can have more practice. Maybe some questions I'll try to discuss with you today, and some other part will be on Tuesday, or maybe with another midterm question that we can set up. Number one is limit. You can try either number one, number two, maybe number one and number two, then number one and number two. And then number three is crazy, right? Yeah, this is number one, number two for now. Okay, you can try first. Number one and number two. Can you try it? I think number one. Okay, number one. Number 1A. I think this is related to your indeterminate form, right? So I think you can start from this one first. Okay, can you try? Yes. Okay. So your teacher is a nightmare.
Only the what the heck? I only have my I don't have the head. Yeah. Yes. Yes. Yeah, 0. No, for A, right? 0, yeah. Okay. Okay, so this can be written as okay. So you could answer this by explaining how the exponent and the polynomial works, which one is faster, or you could try to solve this based on the infinity. We can actually write this in terms of x squared, that is 1 minus x, like that. Professor?
Yes. I think. Well, I'm not saying that it will be, but maybe.
So that means we should study.
Yeah, study hard, study very hard. So we can huh? Yeah, we can actually try L'Hopital rule. Okay, so try L'Hopital rule, and then this will be E, and then somehow you can try some other L'Hopital rule until you get this will be 4 E, and then after very end you get 6, -6, and then -8 E with power of negative 2x. But somehow, if you see from our original limit, you can draw a conclusion that since the E is going to be faster, then it can be 0. You can check from some L'Hopital to give some confirmations that this is going to be 0. Okay. The second question for limit is actually quite simple. If you remember, we have the degree 4 on the top, degree 4 on the bottom. Okay, so we have -1 here and -3. So it should be 1/3, right? Okay.
It's actually divided with the highest degree of x. So with 1 over x is 0, then we can eliminate all 1 over x. How about number 2? Number 2, you need to prove using the differentiability and continuity. Okay? So we have a function. Okay, we have a function that has piecewise. You need to find b and c such that this function will be differentiable. Which means differentiable is going to be need to be first continuous, and second we need to check the limit of that using the limit definition for derivative. Let me erase this for a while. I need to get into. Anyone find what is B and what is C? Idea. Okay. So let me write the question in the new page. Okay, so let me write here. And then let me take this, okay, and then crop. Okay. So first, continuity is when limit. So how do we know the limit is approaching the 0? It's from the interval. Okay, it's this one and this one. Okay, so 0 will be important. So we are going to take that as our x approaching to 0 from the right, and need to be equal from the left. And it should be equal to the function of x. Okay. So first we can check the left hand limit and right hand limit. So suppose that from the right hand is equal with the left hand. So this will be giving you the limit as x approaching, and then the functions will be sin x plus b ln x plus 1, and then plus c. This should be equal to so when we plug in 0, so take 0 inside. So this will be 0, this will be 0 because ln 1, so this will be just c, right? The limit is just c. So we write c. And then limit from the 0 from the left is e negative, it's negative, oh no, not negative, sorry. It's positive. So we take this, we take 0, then e with power of 0 is 1. So we assume that because we want this to be differentiable, so we want this to be continuous. So f of x continuous at x equals 0, so that and c is 1. Okay, so first we get c. Okay. Okay. This is the first. The second, we are going to consider our limit definition. Okay. So at x positive, we are considering that the f prime by definition, this will be f of x minus f of 0. This is x minus 0. So by definition, we get this is sine x plus b ln x plus 1 plus c minus f of 0. And this will be x. Okay. Now I forgot to mention that f of 0, since this is need to be considered as continuous, then if we want to make this continuous, then this will be also equal to f0 should be equal to c, or in our case is equal to 1. So this c and f0 will be cancelled each other. Okay. And then what's next is we can conclude that this will be so we can rewrite this so we can have limit sine x, let me just write plus b and ln x plus 1, and then this is over x. If we put 0, this is 0, this is 0, so it's 0, 0. So I think we may apply L'Hopital. Okay, we may apply L'Hopital. So take L'Hopital. So this will be cosine x plus 1 over x plus 1, or b. Okay. Okay, I think that is the. So we have 1 plus b, right? If we plug in 0, we have 1 plus b. So 1 plus b. Okay. So let me write here, for x positive, we have this f prime. Okay. And now we need to consider at x negative. So f prime x, so we are going to write the same thing, but this is from the left. Okay. So f of x minus f0 so we are going to write e with power x squared. This is minus 1, okay, f0 is 1, okay. And then over x. The same thing here, this will be 1 minus 1, 0, 0. We can also apply L'Hopital. Okay. We can also apply L'Hopital. So we can have 2x e x squared, which gives you the result of 0. So to be differentiable, then I will write f prime x from 0 positive need to be equal with the 0 negative. It means from the right and from the left need to be the same, and it need to be equal to 0, which means that 1 plus b need to be equal to 0. So b is negative 1. Okay, so we get c and b, which is b is negative 1, c is 1. Okay, how about that? Good question, right? Good question. Yeah. Limit, L'Hopital, derivative definition. Continuity only in one question. Maybe I will think what kind of other questions similar to this. Okay, any questions? Any questions? Still loading?
No, but you know that.
Thank you.
Maybe one or two questions. Maybe one or more, two questions.
What the fuck? No, he votes for both.
Maybe I will show you another one. You can see, and maybe if you want, you can choose. Like even I have this. Number 5 is optimization. So I think we can skip, right? Or no? Yeah, this is the largest area. Blah blah blah. We have linear approximation. But I think I will. And then some observation of the graph, okay? And then sketching the curve at the end. Okay, sketching the curve. But I think we need more time for this. Okay. But you can, if you want, you can take this and try later. I would like to go back and maybe number. Do you want number 3 or number 4?
Or 3.
So let's start. Number 4. Let me copy this.
Number 4 is
Okay. So you have the curve. Okay, you have the equation. Number 1, number A, compute dy dx. Number B, find points on the curve with y equal 2. And number C, number 3, find the tangent lines at those intersections from part B. So it's related. But for number 1, it's easy, right? Number A. Number A is easy, or no? Easy, right? It doesn't have like many complications in the equation. So doing the implicit, I hope you get the correct dy dx, the first derivative. So we can start from, let's say A is, let me write the whole equations, x squared y squared plus 2xy equal 8. Okay, so we start with taking all derivative. Okay, remember this x squared y squared, we can think this like a 2 function. This is also the same 2 function, which means we are going to expect a product rule. Okay, so let's take that product rule into this equations. So we are going to have 2xy squared and then plus 2x squared y and then dy dx. and then plus 2, I will write inside here. So y plus x dy dx. And this will be equal to 0. I will grouping dy dx as one group. So this will be 2x squared y, and then plus 2x. And then minus 2y minus 2xy squared. Okay, so dy dx is negative 2y negative 2xy squared over, let me write 2x plus 2x squared y. So we can do something, right? We can do something here. So we can take, let's say, negative y outside. This will be 2 plus xy, okay? I think negative 2y, I think easier, so maybe 1. So 2x, this will be 1 plus xy. So we can cancel this, we can cancel here, okay? So we have negative y over x. So we can fill in the forms. This is negative y over x.
For number B, find points on the curve with y equals 2. So it means that you need to just plug in y equals 2 inside. Okay?
So number B, basically y equal to means that we are going to x squared 2 squared plus 2x and then 2 equal 8. So 4x squared plus 4x equal 8, or x squared plus x minus 2 equals 0. This is, I think, factorizable. So x plus 2 and then x minus 1, right? So we get, the point is when x is 2 or x minus 2 and x is 1. And then we can apply this x with on number C. Okay. So the points will be negative 2, 2 and 1, 2. Okay. So from these points to negative 2, 2 and 1, 2, we need to find the tangent lines. So for number C, we can start, because dy dx is negative y over x, okay? And we have 2 points, which is negative 2, 2, and 1 and negative 1 and 2. Then we can apply each point through the dy dx, so we can get the gradient, the slope, okay? So we can get the slope. This is x equal negative 2, y equal 2. So we have negative 2, oh negative 2, negative 2 or 1. Okay. This is the first one, and for the, so this is for that. And this one is x equal 1, y equal 2. So this will be negative 2, right? So tangent line the first one is m is 1. Okay. So y minus 2, this is x plus 2, or y x plus 4. Second is 4m equal negative 2. So y minus 2 equal negative 2, x minus 1. So y is negative 2x plus 2 plus 2, so plus 4. So that is the answer. So we can write y is x plus 4 and y is negative 2x plus 4.
Okay, right? I found it. Okay, I found it. Too easy, too easy. Oh, or no. So it's taking the how to get a tangent line, taking how to get the implicit differentiation. Okay, later I will put the questions in the Moodle, okay? So you can practice with another question.
Okay, I think
Do one more? Do one more?
how about number 3? Number 3.
How about this? How to solve this? Yes, yes, yes. So every time you have this power with another function, you have function, and then we have another function, we have function, and then we have another function like that. We take the log, to make it. So to make the power goes down. Okay.
In that case, we can change whether y is equal to.
Yes, but I think if I write like this, okay, maybe it will help you. Okay, maybe it will help you. If we have ln h, okay, let me write with h, and then this will be 1 over x, right? Or maybe let me write here. So since we have the ln in the front, okay. So actually, so let me write with ln h, okay. We can take this and then plus ln. Is this helpful?
We can make this happen, and then put here, and then put here, and then derive. I think it will be helpful, right? But don't forget, we still have the ln here. So we take implicit from here. Okay, I think you can try. You can try.
Hmm? The answer is, I think 4 minus ln 2. Perhaps, okay, perhaps. So somewhere along the way, if you think that it's already derived and it's we have like a clear complex, try to input 1. Okay? Some of them will be 0. Okay? Some of them will be 0. Some of them will be 0. And then this h here, we have 1 over h, right? This h, don't forget to take 1 here, and then 1, 1, 1. So you get the h1. Okay, I think that's it for today. Okay? No time left. So yeah. Let me put the QR code, okay?